Okay, so last week we talked about simulation. We talked about statistically significant. Okay, so just a reminder, if you were not here last week, it is statistically significant. Okay. When results of an experiment are unlikely to happen purely by chance. And we talked about that it was less than 5%, right? Okay. So on this problem, you said the following the following is an example of an A/B testing, which is a common data science practice among tech and marketing companies. The marketing team at Yelp came up with two new formats for displaying ads on its site, format A and format B. Before deciding on which format to use across its entire site, Yelp wants to test which format would get a higher rate of ad clicks from users. Okay, so the first thing they asked was calculate the difference in percent of users who click on ads. So how do you go about doing that one? A minus B. So what numbers are going to be that? Okay, so 42 minus 38, which gave you 4%. Okay. All right, so on number one, it should have been 4%.
Yeah, that's what I thought. Yeah, I knew my math was right.
Okay. In your own words, explain what statistically significant means. Before doing further calculations, do you believe the difference you calculated in part A is just statistically significant? So what does it mean? I ask you for words and all of a sudden, like, you shut down. Okay, so let's talk. So it's the difference. Type this so you can read it. The difference in percent from the experiment would be unlikely to happen purely by chance. That's what statistically significant would mean. But because the difference is so small, the results are not statistically significant. So this is probably the hardest thing to wrap your head around because it feels like it's always like opposite day when you write these kind of things out. So read that again and read it slowly, trying to understand what is it saying. If I say something is unlikely to happen purely by chance, what does that mean? Unlikely to happen purely by chance. It wouldn't happen randomly. Something is influencing it to happen. Okay, so I'm going to say that again. If I say something is unlikely to happen purely by chance, I'm saying that something is influencing it to happen. Okay. So because the difference is so small, we said it was like 4%, the results are not statistically significant. So less than 5% are unlikely to happen purely by chance. What's up? So it's unlikely to happen purely by chance. So if it's statistically significant, we have convincing evidence that the treatment caused the difference. So there's not a difference in those two things. So format A and format B. There's no difference between these two things. So format A, is there anything that's impacting it? But like looking at the two different clicks on the ads, they're very, very close. Is there a reason why?
Not good.
Not,
The upside is not good.
okay.
The ads are good.
Hmm.
But they're not working.
So since they're both, it's so small, so it's unlikely to happen purely by chance. So is there something impacting it, or is there not something impacting it? Are we sure? This is where stats starts getting a little iffy. So I need y'all to think about this. This is not one of those like you can just walk in here and just do random things. Read it again. What's your definition of statistically significant? Read it on your paper. You wrote it up at the top. When results of an experiment are unlikely to happen purely by chance. So if it's less than 5%, is it statistically significant? Go ahead. Yes. So is this necessarily going to be that they are statistically significant based off of just this result? Why did I say that it's not statistically significant then, if it's less than 5%? Because what? Say it again. No. Look at your sample size. We did 50 over here. We did 50 over here. Is there going to be that big of a difference when we're sampling 50? Probably not, right? Look at the difference in how many people there are. That's 21 versus 19, yeah? So are these statistically significant results? No, even though it's less than 5%. Guys? Okay, it gets a little tricky right here. Okay, so stay with me. Okay. All right, look at number 3. The following simulation was performed assuming format A and format B are equally effective. The individual outcomes from this experiment, click or not clicks, were randomly sorted into 2 groups. The percent who clicked were calculated in each group, and then the difference was taken between the 2 group percents. This was repeated 100 times. The resulting differences in percents who clicked are displayed here. Using the results from the simulation, do you believe the difference in percent of users who click between formats A and format B is statistically significant? Why? Again, dead so. Whew. Okay.
I'm not bragging. I'm sorry.
All right. So what's going on in this data? What does this actually represent? Okay. The difference over 100 trials. Okay, so each dot represents the difference between the 2 groups. Okay, each dot represents the difference between the 2 groups. Now there is 100 dots here. Okay, everybody with me? So the simulation was done 100 times and they found the difference between the 2. So what are we going to say here? Why? Majority is between -5 and 5. So you're saying because it's in here?
Yes.
Okay. Here's 5%, right? Right, like here. And we've got this and over. Because how much did we calculate in part 1? Oh, part 1. 4%. Okay, so 4% is right here, right? Yeah. So if you counted up all these dots, I'm going to go ahead and help you with this. There are 42. 42% of your data is bigger than 4% or equal to 4%. 42% of your data is greater than or equal to 4%. So do we think that there is a statistical significance? No, because 42% of the time we would get a difference of 4% or more purely by chance. Yep. So okay, so we found in part 1 that in our first simulation, it was 4%, right? Okay, so we're going to draw that on our little graph, okay, because that's kind of like our baseline, okay? Then we counted up how many dots were on the right-hand side, because if it's greater than 5%, it's not statistically significant. If it's greater than 5%, it's not statistically significant. Cool. So we have 42% of our data that's greater than that 5% or greater than our 4% and up, right? So it's not going to be statistically significant because 42% of the time, it's happening purely by chance. It's greater than that 4%. So there's a big difference between those two. Yeah. Okay. I want to practice more of this because I know it's tricky. Okay. It's like I'm saying opposite day every single time. Okay. So go ahead and look at your homework that you just got. If you didn't get it, I'm giving it to you right now. So the homework that you just picked up a second ago. Go ahead and take a look at, let's start with 4.8. So find 4.8. And again, if you don't have it, I'm going to get to you in just a second. All right, we're going to spend like maybe 15 minutes on this. And then I'm going to do some review for your test tomorrow. Yeah. Okay. So 5 pages. Okay, so you should be on 4.8. Okay. A recent study by Microsoft in Japan investigated impacts of moving a 4-day work week. In the study, they gave all of their employees 100% of their pay to work 80% of their usual hours. Microsoft reported a statistically significant increase in productivity compared to the same time period the previous year. Okay, so everybody understands the concept. What is the meaning of statistically significant in this context? So, say it again. Okay, so statistically significant means the observed change in productivity. Right. It would be too high to attribute by chance. It's too high to attribute to just chance. Something influenced it to happen. Statistically significant means that something is impacting it. Statistically significant means the observed change in productivity is too high to attribute by chance. Does that make sense? Go ahead. And the difference? Have you looked at, so if I have they said that there was an increase in productivity, right? Okay, so the difference between those two, is it going to be greater than 5 or is it going to be less than 5? Right. So is it happened purely by chance or was there something that influenced it? Right. So something has influenced it to make this data significant enough where it's not happened purely by chance. Okay? Just say that. Say that. Okay. Let's look at part B. Using what you know about experiments, what is one way to improve the study? Why would this study be challenging for Microsoft? So what should they do? Say again. Have two different groups. What else?
They assigned them to the
Okay, but what would be bad about that? Like,
people who does.
okay, so you have your two groups of 5-day work week and a 4-day work week. If I'm in that 5-day work week, I'll be mad, right? So maybe doing something to make sure that that doesn't happen, where there's like a jealousy or, well, I'm working 5 days, so I'll just put it off until tomorrow. Does that make sense? Like there might be some influence there. So I need to make sure that they don't let people know what's going on. Yeah. All right. Let's look at 2. Again, the more we do these, the better it's going to be. I promise. Embrace it. Okay. According to pregnancy tracking apps, there are a few predictors to determine a baby's biological sex before the anatomy scan at 20 weeks, but do they actually work? One example is the ring test, where the mother holds a dangling ring attached to a thread or string over the belly. If it swings in a circular motion, it's a girl. If it moves back and forth like a pendulum, it's a boy. Suppose we sampled 100 women who did the ring test prior to giving birth, and 56 of them predicted the sex correctly. Okay, so first of all, how many predicted it correctly? What's our proportion here? 56 divided by 100, which is 56% or 0.56. A simulation was performed under the assumption that someone is just guessing.
Yeah.
The graph shows the results of 200 trials of the simulation. Okay. Each one of these dots represents one simulation, right? Of correct number of guesses. Okay, does everybody understand what's going on in context? Okay, now what does dot above 61% represent? 61% of correct guesses done during that simulation. Okay, because remember, each dot represents one simulation. What percent of the 200 trials resulted in a percent correct of 56% or more? 12%. You would count up 24 and divide it by the 200, and that would give me 12%. Okay, this will help a little bit. Do the results from our sample of 100 women and the simulation provide convincing evidence that the ring test is better at predicting the baby's sex than just guessing? Why? Okay, you don't know why, but you got the right answer. Okay. Okay, why? How many trials did you, out of the 200, how many were above the 56%? Okay. So, so you're saying no, there's not convincing evidence. that the ring test is better than just guessing. And that's because 12% is bigger than 5%. Right? Remember, 5 is our like number for statistically significant, right? So what sample results would convince you that the ring test is an effective predictor of the baby sex?
1. We're above 55.
If it was above 55%? Why do you say that?
Because if our 50-50 is 50, and we have that 5%, I forgot what the word is called, plus 5 minus 5,
Margin of error.
margin of error, then anything above 55 would be considered significant. Oh, well, if majority is above 55, that would be significant.
Okay, but we just said if 56% or more, right? Like on this last one, we said, is there convincing evidence that the ring test is better than just guessing? We were talking about 56 or more, right? So what sample results would convince you that the ring test is an effective predictor of the baby's sex? It's gotta be like bigger than 56, right? Look at your data. Okay, what would be 5%? What would be like 5% of this data? If I did 200 simulations, 10, right? So then looking at this, I would got 1, 2, 3, 4, 5, 6, 7, 8, 9. Somewhere in here, right? Do you see it? Like 59% or more, right? Okay, so 59% or greater. So we would be convinced at this point that the ring test would be better than just simply going, I think it's a boy or a girl, right?
Not binary.
All right. Letter E, if we instead sampled 500 women and again 56% correctly predicted the sex of the baby with the ring test, would we be more convinced or less convinced of its effectiveness? More. Why? Okay, larger sample and variability decreases. So there's not a bigger range. It'll be more true to like the true proportion that are correct guesses. Are we okay? Little bit better. Okay, try number 3. All right. So we're talking about consuming peanut products. Okay. We're talking about peanut allergies. They monitored children. 17.3% of the group who completely avoided, and then 3.2% who had regular exposure. What type of experiment is described? Oh, what?
Question?
Longitudinal
Interesting.
So is it random? Were they assigned randomly, right?
Convenience sample?
No.
Yes.
Convenience. What? So this is going to be a completely randomized design. Okay, I know on a multiple choice question you would have gotten that, right? Okay. Randomly assigned. It doesn't state how they were assigned. It doesn't give us any details on it, but we know that it's a completely randomized design, right? That's all we know. All right, identify the explanatory variable. Explanatory, what is it? Okay, so level of exposure, and then what's the response? Okay. So exposure, and then whether or not they have the allergy. Okay. Calculate the difference in the percent. Okay, so you should just subtract. So 17.2 minus 3.2 equals 14.1. All right, everybody good on ABC? A statistical test determined the probability of observing a difference in the percentages this large or larger purely by chance is less than 0.01, assuming there's no difference in the development of peanut allergies. Crap. Sorry. Does this probability provide convincing evidence that early and regular exposure to peanut products will reduce the likelihood of developing a peanut allergy? Why? Oh, you gotta give me something other than logically. Okay, so yes, there is convincing evidence. Why? Okay. Why does that matter?
I'm tired. I cannot, my brain cannot. break.
Okay, so they don't just happen purely by chance. There's a big difference between the non-exposed and the exposed. Agreed? Yes. Okay, so there's a difference. So do we have convincing evidence? Yes. Okay, so these results are too unlikely to have occurred. So we do have convincing evidence. Yep. So when it states that it's 0.01, it's giving you the statistical significance of that. Go ahead.
Is that 5%?
Yes. Okay, we're eventually going to talk about something called an alpha. And sometimes it's 5%, sometimes it's 1%. It just depends on the scenario. Okay, they gave us that, right? Okay, we okay? Getting there? Okay, maybe. All right, go into the page, or I'm sorry, go to number 4. All right, yep, go ahead and try number 4. These are the questions that you don't like. So let's try number 4. All right, ready? Take like 2 minutes. Go. Oh, okay. Take a pack of 52 cards. If my client is innocent, it is a normal pack of cards, so 13 hearts. If my client is lying, it's a fixed pack and all 52 cards are hearts. I draw the first card and it's a heart. Aha, guilty. Well, obviously common sense tells us that it's not the case. There was 1 in 4 chance that this would happen even if he was innocent. We don't have statistical significance just from looking at that 1 card. Okay, does everybody understand? Okay, so I draw a second card, another heart. Definitely guilty then. Well, there were still 12 hearts in those remaining 51 cards, so not impossible. The math, 13, not yet, tells us that this happens about 6% of the time, even if he was innocent. So for most scientists, this still would not count. So that's not enough evidence. Okay, we draw a third card, another heart, the 3 in a row. The chances of this happening would be 0.01294. So just over 1% of the time, this could happen by chance. Everybody got it so far? Okay. In much of science, 5% is the cutoff. So if you have no other evidence than those 3 cards, you have a statistically significant result that he is guilty. Yes. Okay, so the important part is that the cards you're allowed to look at better your confidence that he is guilty, which is another way of saying the higher the statistic significance becomes. Does that help? Yes, no, maybe. Okay, so we do one card. That's not enough evidence, right? You're not convinced. Two cards. Still not convinced. Because look at the percentage. That's over 5%. That's over 5%. Yeah? So we keep going until we go, hey, this happened purely by chance, and he's guilty. Yeah? I know it's hard. I don't expect you to get it today. Okay? All right, cool. Okay, let's go back. Let's look at, we all on 4? Okay, identify the treatments. So what are the treatments in this scenario? The 4 exercise programs, right? So aerobic, resistance, combination, or none, right? Okay. What's the purpose of including a group who did not complete an exercise program? Okay, there's a control. All right, part C. The results determined there was statistically significant difference in the CVD risk profiles for subjects who completed the aerobic program and the combination program compared to the control group. Explain what this means in context of the study. So what does this mean?
I CVG risk profile or another.
Okay. So we would say that the observed differences in CVD risk profile between aerobic and control groups and combination group were too large to attribute to chance alone. Okay, on D, the difference was not statistically significant for the resistance only group compared to the control group. Explain what this means in context of the study. So the observed difference between groups was not large enough to rule out chance alone as a possible explanation. Okay. Okay. All right. Let's chat about, but pause. You need to be able to tell me the sample and the population based on a scenario. You need to be able to tell me which is the best sample method. Okay, so you need to know all the different sampling methods. Talk to me about bias. Be able to identify treatments and how many are occurring. You need to know what a blind experiment is and like how to use it, who is blind, what's a single blind or versus a double blind. You know about matched pairs. matched pairs. Sorry, it's getting worse. It's fine. Randomized block design. Randomized block design. Okay, so what do you need a block for? Understanding conclusions. Systematic random sample. Explanatory versus response variable. Explanatory versus response. And also, is this an observational study versus an experiment? What are confounding variables? And then there's one question about statistical significance. You're welcome. Okay. So treatments, experimental units, response variable, and then statistically significant. Look at that awful handwriting. So sample and population, be able to identify it. Sampling methods, bias, blind experiments, match pairs, conclusions, systematic random sample, randomized blocking, explanatory versus response, and then being able to identify treatments, units, response, as well as statistically significant or not. Okay. So here's what I want us to do. Okay. Go ahead and take out your, yeah, we got a little bit of time. Go ahead and take out your laptop. Okay. And you are going to go to AP Classroom. Yeah. Still not on there. Dang, man. Okay. So you're going to go to AP Classroom and there is a progress check. It's in MCQ Part B. Y'all tend to like do worse on your MCQs because you're not slowing down to read. Okay, so I need us to actually slow down and read. Okay, so you're going to do your MCQ Part B. Okay, MCQ Part B. What's up? Yeah, that's fine. Okay, if for whatever reason you're not on the AP Classroom, I will put up the codes in just a second. Student video.